I might call these 6 functions parent functions because they're relatively simple and straightforward. We've got the absolute value function, x squared, x cubed, square root, cube root. I want to call these parent functions because each one of these functions has a location scale family. And a family of functions is just a set of functions that have something in common. And the thing that these have in common is that every function in the location scale family is going to have exactly the same shape of the curve, but it's just going to be stretched or squished or moved up, moved down, moved left, moved right. It's going to have some kind of transformation happening to it. So take any one of those functions, any one of those parent functions, and then you also, if you go on Desmos and you type in something like this, you can see what the location scale family of functions looks like. So those A, B, C, and D letters, those represent just constant numbers. And those constants are going to determine the location and scale of the curve. And please do this at home, right? I'm going to do this in class as a demonstration, but I really want you guys to get on your computer at home, pull up desmos.com, and type this in. I think it really goes a long way for understanding the topic today. More than other days, it's very important. So if my parent function is the sine function, and again, it's not really important the details of what function this is, I just think sine is a pretty function that works well with these transformations. But the location scale family would be a constant c times f of x minus a over b plus d. So if I were to make a equal to 0 and make d equal to 0, then this is the function I'm starting with, right? This is my parent function. What would happen if I wanted to take this function and slide it over to the right a little bit? All I would need to do is change my a parameter. And if I increase the value of a, this function begins to slide on over to the right. And that's what happens for positive values of a. So I'm doing x minus 6 right now. But what if I have a negative value of a? What if I'm adding something to the argument? Then, if I add something to the argument, I'm sliding it to the left. Okay? So that a value determines the horizontal location. What does b do? If I divide by a number b in the argument of my parent function, then that's going to stretch it out in the horizontal direction. The larger b gets, the more stretched out it gets. If I choose to find a value of b that is between 1 and 0, then it's going to squish it so that my new function is a squished version of the parent function in the horizontal direction. Okay. What if I make c, the constant out front, what if I make that larger? Then I'm going to stretch this function out in the vertical direction. And if I choose a c value between 0 and 1, like a really small c value, that's going to squish it in the vertical direction. What happens if I choose a negative c value? If c becomes negative, it's going to flip and become a mirror image, right? This is negative 1, right? It's reflected across the x-axis for negative values of c. And then lastly, what does d do? Right? D is the number I add on to the very, very end. And adding a number to the end is going to move my function up, and subtracting a number from the end is going to move my function down. Okay, so these values change the location and scale of the curve. And another funny thing you can do in Desmos is you can hit the play button and you can just, I don't know. Ooh, yeah. Anyways. Very neat. So try that on your own. Spend some time trying to understand this. That's why I put it on your homework, is to really encourage you guys to try Desmos out if you haven't already. So, if you have a parent function, like the function x cubed, you should be able to write another function that we might call g of x that represents the same exact curve but with this kind of transformation. Like, how would I take this x cubed function and slide it up by 2 units? I would write x cubed plus 2. Yeah. Okay. What if I wanted to write a new g function that's the same as my parent function f, but I slide it down 4 units? What do I write? X cubed minus 4. What if I want to write the same as my parent function, but I want to move it to the right by 1 unit? Yep, Brianna's right. This is parentheses x minus 1 cubed. So if I subtract something from the end, it moves my curve down. But if I subtract something from the argument, like this time, that's going to move it to the right. Next step, how do I write the same thing but move it left by 5 units? Yeah, x plus 5 moves it to the left. What if I want the same as my parent function, but I want to reflect it across the x-axis? Yeah. If I want to reflect it across the x-axis, I just have to make it negative. What if I want to take the same function as my parent function, but I want to reflect it across the y-axis? In that case, I put the minus sign in the argument. Okay, I realize that negative x cubed is the same thing as negative x cubed. But that means, for this particular parent function, reflecting it across the x-axis is the same as reflecting it across the y-axis. That ends up being true for any odd function. But if you have you got the x cubed curve and you reflect it across the x-axis or across the y-axis, you get the same result. But that's not always true, right? Other parent functions, that's not going to be true. So the difference is reflecting across the x-axis means you put the minus sign out front. Reflecting about the y-axis means you put the minus sign in the argument. Okay, I'll rewrite my parent function over here. And let's say I want to take the same function, but I want to stretch the curve in the vertical direction by a factor of 2. What do I do? So if I write 2x cubed, now every point along the curve is going to be twice as far away from the x-axis. I'm stretching it out in the vertical direction. How would I squish the curve in the vertical direction by a factor of 1/3. Yep. So if I multiply by 1/3, just like I wrote down, now every point along the curve is going to be 1/3 the distance away from the x-axis. So it's going to get closer, it's going to get squished in the vertical direction. Okay, how do I stretch the curve in the horizontal direction by a factor of 3? I'm going to divide by 3 in the argument. That is going to stretch this out horizontally by a factor of 3, so that all of the points on the curve are the same, except they're going to be 3 times as far away from the y-axis. So pull it out. Lastly, this is the last transformation you need to know. If I want to squish the curve in the horizontal direction by a factor of 1/2, I might write x divided by 1/2. But you'll notice that's the same thing as writing 2x cubed. And so in this case, all of the points are going to be half the distance away from the y-axis, so everything's going to get scrunched up horizontally. And that's it. So there's 10 transformations that you need to know in order to make this work. Do you have any questions so far? Okay. Again, please get on Desmos and try this out for yourself. You can verify that it works. The next thing I'll say is that the order does matter, because we're going to work some problems here in a second where you'll have 2 transformations or 3 transformations. And if I've got a parent function and I want to move it to the right, and then I want to stretch it in the horizontal direction, and then I want to reflect it across the x-axis, and then reflect it across the y-axis, and then squish it in the vertical direction, and then move it down, then it matters the order in which I consider those transformations. And this is the order. First off, consider if you're going to slide this to the right or to the left. That's the first thing you got to think about. Am I adding or subtracting something in the argument that's going to move this to the right or to the left? Then you need to think about, am I stretching or squishing or reflecting this in any direction? And once you've taken care of that, only then should you think about moving this up or down in the vertical direction. You've got to respect the order, otherwise you'll get something different. And with respect to that order, we're going to do some examples now. So this is how a test question might look, right? It says, graph the following function and state the transformations. I'm going to give you what the parent function looks like, right? So the parent function is already shown on the graph. It's x squared. And the question is, how do I go from the parent function to my new function, g? What's going to be the difference between f and g? Perfect. The only difference is that we're moving this curve to the left by 3 units. So if I want to graph this, I just have to take all of these points and scooch them over to the left by 3 units. And that's it. That's super easy. New example. Again, I'm going to try to go from my f function to my g function. This time my f function is the absolute value function. And my g function is 1/2 times absolute value of x minus 5. So as I'm thinking about the transformations taking place here, I see 2 things that are different. one thing is I'm multiplying by half, and the next thing is I'm subtracting 5. So think about the order, right? I think, am I moving this to the left or to the right? No, I'm not moving it to the left or to the right. Am I stretching this or squishing this or reflecting this at all? I'm squishing this down vertically. I'm squishing it down in the vertical direction by a factor of half. So if I were just going to graph the curve 1/2 absolute value of x, I would draw it like this in green, where all of the points are half the distance away from the x-axis. And then the next transformation I do is I want to move it down 5. So now take the green curve, and if I actually want to get my g function, the difference between the green curve and the orange curve I'm about to draw is I just move everything down 5 units. So if you have to do more than one transformation, like this time I had to do 2 transformations, it helps to draw all of the intermediate graphs, right? Like it's okay to draw the green graph and the orange graph. I mean, as long as you remember the orange graph is your final answer. Okay? Make sense? I say the order matters, right? If I had moved that blue curve down 5 units and then moved all the points half the distance to the x-axis, I would end up with a different answer, right? You'd get the wrong answer if you did those transformations out of order. And so that's why we move horizontally, and then we stretch and squish, and then we move vertically. Okay, here we go. I've got a parent function square root of x. And I want to eventually get this function, square root of negative, parentheses, x minus 5. The first question I ask is, am I moving this to the left or to the right?
Right 5.
I'm moving it to the right 5 units. Let me choose a different color. Move right 5. And if I move right 5, I'm going to get a curve that looks like the square root of x minus 5. Okay? What's the next thing I need to do? Reflect across the x-axis or the y-axis? The y-axis. If I want to reflect across the x-axis, I would put the minus sign out front. But if I want to reflect across the y-axis, I put the minus sign in the argument. And so this is actually going to give me the g curve, which is the square root of minus x minus 1. And so then I put it over here, like that. Again, order matters. If you had started off by reflecting the blue curve across the y-axis and then moved it right, you would get something that looks like this, like totally different. So do everything in the right order. One more example of this question type. I want to start with my f function and move on to my g function. And this time, I don't tell you what the f function is, because it doesn't matter, right? We're just calling this function f of x, and you can see it graphed there in blue. And what I'm going to do differently when I graph g is 3 things, right? I'm going to multiply by 3, I'm going to divide x by 2, and then I'm going to add 5 to the end. So am I moving this to the left or the right? No. Am I stretching or squishing this? I'm going to stretch this horizontally, right? So step number 1, stretch horizontally by a factor of 2, yeah. And that means every point along this blue curve is going to be twice as far away from my y-axis. That point's going to be twice as far away. This point is twice as far away. That point is twice as far. That point is twice as far. You get the idea? And I'll draw this nice orange curve. And this is not my final answer. It probably wouldn't go up at the end, it would probably go back down. This is not my final answer, but this would be the curve y equals f of x over 2. The next thing I'm thinking about is that 3. What does that 3 do to my function? Yep, it's going to stretch vertically by a factor of 3. That means every point along this orange curve is about to get 3 times as far away from the x-axis. So it'll look like this. The green curve is going to be the same as the orange curve, but now every point is 3 times as far away from the x-axis. What's the last thing I have to do to finish this problem? Yeah, the plus 5 at the end is going to move this thing up 5 units. So the purple curve is going to be the same as the green curve, but I'm just moving it up 5 units. So here's 5 units up. Every point from the green curve gets scooted up 5 units. And this will be my final answer when I'm done drawing it. Okay. Questions? Super easy. So these aren't hard questions if you know what the transformations do, right? It's going to be just a struggle to memorize what each transformation looks like in the formula. The other kind of question I'm going to ask you next week on your test is this. I'll give you what the curve f looks like, and I'll give you what the g curve looks like, and I'll even tell you that the function f is x cubed, but then we're going to ask you to write the formula for g. How is this g curve different from the f curve? I'm moving to the left how many units? 4. And then I'm moving down how many units? 1. So my g function should be this is my final answer. The plus 4 moves it to the left, and the minus 1 moves it down. All right, this is my last example for the day. So here's my g function. I eventually want to be able to write what the formula is for that curve. And then here is my f function. F is just the cube root of x. What is different about the red curve? Move up how many units? 4. And then we're also going to move 2 units right. So what does this formula look like? X minus 2 plus 4.